Any questions? Have you had a chance to go through that section that I asked you to, curvilinear coordinates?
Yeah.
Did it make any sense? No? Okay. Just a quick recap of what we did and what are the important things that you should remember. I always put this from a previous lecture. So when you are reviewing, at least make sure that what is in that is understood so that it will be helpful for the subsequent lectures as well as the assignments. So we saw in the last lecture how to calculate the force on a surface given the normal to the surface and the stress acting on that surface. We first saw that when that stress was just pressure. Pressure is a normal component of the stress. When it is a tangential component, it's a shear stress. Then the way that you calculate it is simply taking the dot product locally on that surface. And then you set up an integral to find out the total force. And then we introduce the index notation. How many of you feel lost with the index notation? That's good sign. So you're not lost. You understand it. And there is this ED rule which allows you to prove identities and stuff like that in going from a cross product to a dot product, etc. And we reviewed what a dot product is, what a cross product is, what a dyadic product is for both algebraic expressions as well as differential expressions. For differential expressions, they give rise to the gradient, divergence, and curve of an operator operating on certain quantity. And then we looked at the integral formula, which is generalization of integration as well as the Leibniz rule. So those two are going to be important today in today's lecture, for example, when we develop the equations of motion. So you should review those and make sure that you are comfortable in understanding what it means. I'm not going to ask you to prove in this course any of those expressions that are given there. Simple identities like the ones that in your current assignment, yes, they will be part of the midterm and final exams. And then in the last lecture, I asked you to look at curvilinear coordinates and go through that section, the idea basically of a metric tensor. And we will see what is the usefulness of such a generalized approach to developing these curvilinear coordinates. A simple example is a spherical coordinate, which is given on the right-hand side figure. Okay, so in general, the basic idea with curvilinear coordinates is if you are given a set of coordinate x1, x2, x3, and you want to transform physically meaningful quantities in those coordinates. These could be position vector, so that the same point will be addressed by two independent coordinate systems. Okay? So how do we do that? So the point remains the same. The location itself is the invariant thing, but the components will be different numbers, the set of three numbers in the two different coordinate systems. Velocity vector, for example, is a physically meaningful quantity, okay? But its components will be different in different coordinate systems. In the same sense, the stress tensor is a physically meaningful quantity. So we should learn how to expand these in various coordinate systems or how to transform them from one coordinate to another coordinate. So we're going to call the new coordinate as Q1, Q2, Q3. They are called curvilinear coordinates because what is the basic idea of a coordinate reference frame, Cartesian reference frame? If I go along this axis, only x1 is going to change, x2 and x3 are going to remain constant. Okay? So if I take, for example, another point in the x2, x3 plane horizontally, once again x1 will change, but x2 and x3 will remain constant. So in the same way, if I'm going in the x2 direction, x1 and x3 are going to remain constant. So each direction, only one variable is changing, the other two are constant, and they allow us to address any point in a three-dimensional space. Okay? The same idea applies to spherical coordinate system. Okay? For a spherical coordinate system, for example, the coordinates are r, theta, and phi. The three numbers. Okay? And that covers the entire space, three-dimensional space. And if you give me these three numbers, I'll be able to reach a particular point that I want you to reach. So on such a coordinate system, if I keep r constant, change theta and phi, what kind of surface would I get? Let me maybe go back to the Cartesian frame that is still familiar to you. Suppose I keep x1 constant at a point, and then I change x2 and x3. What kind of surface will I get? A plane, right? A plane that is perpendicular to x1. Okay. So in the same sense, now if you understand that idea, ask this question yourself. If I keep r constant in a spherical coordinate system, what kind of a surface will I get? A sphere, right? And spherical objects are very commonly found, and that's why spherical coordinate system finds use in describing conservation laws that apply to objects that are in a spherical coordinate system. In such a spherical coordinate system, if I keep, for example, change r, you have to understand this. So here, this is a theta, okay, and that is going from x-axis to the y-axis. Go there, because I lose the sound. So this is the phi axis, and the theta axis is from the vertical axis z. It's measured from there. So if I keep a constant theta, but change phi and change r, what kind of a surface will I get? A cone. It's also given there. Okay. So each coordinate, when you keep one coordinate constant and change the other two coordinates, describes a surface. Okay. And these surfaces intersect. In the Cartesian frame, these planes intersect. And when three planes intersect, it gives you a point. When two planes intersect, it gives you a line. So in the same way, when three surfaces intersect, you get a point. When two surfaces intersect, you get a curve. Not a line, but a curve. Okay? Not a straight line, but a curved line, you can say. Okay? And that's why it derives its name as a curvilinear coordinate. So we are describing Q1, Q2, Q3 as three arbitrary curves that could be perpendicular to each other, meaning at every point they intersect. If the tangent to those curves are perpendicular to each other, then we call such a system as orthogonal curvilinear coordinate system. The Cartesian frame clearly is an orthogonal system, right? At every point that the three axes intersect, what is the angle between them? 90 degrees. Is that true for a cylindrical coordinate system? How does a cylindrical coordinate system look? Let's draw this. Maybe let's go to the separate. A cylindrical coordinate system will have r, theta, and then z as the three coordinates. Okay, r, theta, and z. Now, on such a system, what would the constant r surface look like? A cylindrical surface. How would a constant z surface look like? A plane, right? How would a constant theta surface look like? You're doing well, but I want to make sure that others catch up. Okay? So, what would a constant theta surface look like on a cylindrical coordinate system? What do we mean by a constant theta surface? So, you measure a constant angle theta, and you can change r, but all the radius should have the same angle. You can change z to be anything you want. So what would such a surface look like? It's a plane, but it's a plane passing through the z-axis. Whereas a constant z surface, I asked you earlier, would be a plane that is perpendicular to z-axis. Okay? So the question I was actually going to ask you is, in such a coordinate system, at every point, I will have an r line going through, a theta line going through, and a z line going through. Okay? What would be the angle between them? Will it be orthogonal? Will it be perpendicular? Okay? So for example, I take a point here. The theta coordinate is this. Theta is changing along that curve. If I draw a tangent to it, is that theta line going to be perpendicular to the r line? Obviously yes, because it's a circle, right? Is that going to be perpendicular to the z line? It's going vertical up. It's going to be. So the cylindrical coordinate system forms an orthogonal coordinate system. At every point of intersection, the three coordinate lines, curved lines, in this case, some of them are curved, some of them are not. Okay, but the three coordinate lines intersect at 90 degrees to each other. When that happens, we say that it is an orthogonal curvilinear coordinate system. For spherical coordinate system, also it occurs, the same thing. So it is an orthogonal curvilinear coordinate system. Now, any questions on what we have talked about so far? Okay, what we are going to get at is a way of expanding the divergence, the curl, the gradient, all those operators in any coordinate system that we choose. That's a skill that you should have. It's just a mathematical skill that you should develop so that you can write these equations in any coordinate system. Even though we'll be using primarily cylindrical and spherical coordinate system, Cartesian of course, there are situations where you may have to learn how to expand it in other coordinate system. Now, how do we develop this ability to expand all these terms, the divergence, gradient, etc., in any coordinate system? We keep things that are constant. That is, a point position vector is invariant, velocity vector is invariant, stress tensor is invariant. Using that, we try to develop what is the relationship between these two coordinate systems. Here is the way that we are going to approach this is by saying x1, x2, x3 are Cartesian frame, q1, q2, q3 are some orthogonal curvilinear coordinate system. There is a relationship between them. And that relationship, in an abstract sense, we are going to write it in this form. Okay? That is, qi is some function of xj. Similarly, the inverse, xj, is some function of qi. I'm going to give you an example later on. If you have seen that, you will follow it very quickly for cylindrical coordinate systems. But in general, if there is so when I write this equation, qi equals qi of xj, what does it mean in index notation? How many equations do I have? I is a free index, so I have three equations. Okay, and each one of those qi is a function of each one of those xj's, x1, x2, x3. So basically, if I'm expanding this, the way that I should write this one is saying q1 as a function of x1, x2, x3, q2 as a function of x1, x2, x3, q3 as a function of x1, x2, x3. So if you give, what does this algebraic relationship tell you? If you give me three numbers x1, x2, x3, these three equations will allow me to calculate q1, q2, q3. Similarly, if you give me q1, q2, q3, I should be able to go back and calculate x1, x2, x3. That mapping between x and q should be unique, so that you have a unique coordinate system representation. Okay, in such a system, if I have 2 points that are close to each other, then I can define a distance between those 2 points. Okay, the first thing is that the point should be the same invariant point P, and then if I have another point Q, this distance I'm going to call it as ds, the arc length, small differential arc length between P and Q. That distance, whether I measure it in the x coordinate system or I measure it in the q coordinate system, it should be the same, right? We want the point to be the same, we want distances to be the same. Just because I'm using one coordinate system and you are using a different coordinate system, measure of distance doesn't change. Okay, so that is the idea that we are going to use to relate the derivatives or the rate of changes in one coordinate to another coordinate. So in Cartesian frame, how would you write that? that differential distance. x1, x2, x3, and I have a curve, small curve ds. If I ask you to find out what is the expression for that arc length ds, it's an arbitrary straight line. If in a two-dimensional case, you can probably easily see it. If I have only x1 and x2, and I have a small distance ds, okay, and so this is dx, and that is dx1, that is dx2. What will be ds? Pythagoras theorem, right? dx1 square plus dx2 square. So in this case, you will say ds square is equal to dx1 square plus dx2 square, using simply the Pythagoras theorem. So the same thing is applicable in the three-dimensional case, where in the three-dimensional case, the ds square will be equal to dx1 square plus dx2 square plus dx3 square. It's a three-dimensional curve, okay? And that is exactly what we are writing in this one. So when you read that before this lecture, you should understand what we mean by dxi, dxi. Summation is implied because I repeats here, okay? So that actually means ds square equals what I've written here. They are exactly the same. I'm just writing it in a compact index notation. Okay, but we know that each one of xi is a function of qj. There is a relationship between x and q. So I can write dxi as dxi dqj dqj. What rule am I applying here from calculus? Chain rule, right? Chain rule simply says that the differential change in x1, when x1 depends on q1, q2, and q3, I have to once again expand this one. So when you expand this one for example, dx1, we are saying that is equal to dx1 dq1 dq1 plus dx1 dq2 dq2 plus dx1 dq3 dq3. That means x1 can change by changes in q1, q2, or q3 because x1 depends on all three of them. So this is the chain rule that relates what happens in the x coordinate to what happens in the q coordinate. These are the two coordinate systems that we are relating. Okay, any questions so far? Now we are saying, okay, I'm going to take this and replace it in here and in there. Okay, so this is the first one, and this is the second dxi. Okay, so I'm simply replacing that dxi that appears twice, but I want you to carefully note and explain to me why I chose the indices that I did there. Why did I choose, for example, the first case, dxi, I put dqj, dqj. In the second case, I have still dxi, but this time I put dqk, dqk. Why did I do that? Exactly, you cannot repeat more than twice. Okay? So already a summation over j is implied there, and I need to indicate that there is another set of summation over k. Okay? So the dxi appears twice, and I know the relationship between dxi and dqj. Okay? This is also the same. For example, I could write this also as dxi dqk dqk, because the repeated index is you can use any symbol to indicate that it is repeated over that index. Okay? So they are the same. But when I'm using it in a product, I need to make sure that I don't repeat this the same. So I'm using j in the first one and k in the second one. So what is the resultant? Now we really have a very messy expression. dxi dqj, dqj, dxi dqk, dqk. What is the resultant of this? Is it going to be a scalar, vector, or a tensor? Scalar? It's going to be a scalar because obviously the left hand side is a scalar. Right? There is no free index in the left hand side. We are measuring distance. Distance is a scalar number. Right? So the right hand side should be a scalar. So there is actually 3 indices that appear there. I appears twice, j appears twice, k appears twice. So when I expand that, I'm going to get how many terms? 27 terms. Right? So it's a very compact way of writing a very large expression. Okay? But in all this, we know how to calculate these derivatives because we know the algebraic relationship between x and q. Okay, that is what is given. Our starting point was that we know this. If you give me x, I can calculate q, or if you give me q, I can calculate x. That relationship is known. So I can take the partial derivative of those and I can calculate. So this quantity is rearranged as gjk times dqj dqk. That is, I'm combining these two terms and writing it as dqj dqk, and gik is what is called a metric tensor. Okay, so gik is, as I've written here, this is dxi dqj dxi dqk. That's a second order tensor because there are 2 free indices there. Okay, so it is the metric tensor that allows us to go from one coordinate to another coordinate, keeping the distances the same. So the point is the same, that is given by xi equals qj, and the distances are the same, is enforced by the metric tensor. Metric means what? Measure. Okay, the metric tensor makes sure that the measure of distances are the same in the 2 coordinates. And sometimes it is called the structure of the tensor will tell you whether it is orthogonal. We talked about orthogonality. What does it mean? Whenever 2 coordinates intersect, they must intersect perpendicular to each other. When that happens, you will find that the metric tensor is diagonal, meaning whenever j is not equal to k, that gjk will be equal to 0. And otherwise, it will be on the diagonal elements, you can calculate all the partial derivatives, dx1, dq1, dx2, dq2, dx3, dq3. So there will be 3 metric coefficients, h1, h2, h3. And we define the metric coefficient by this expression. Now, an excellent exposition of this is given in the book by Happel and Brunner. If you want to learn more about orthogonal curvilinear coordinates, there is an appendix A, that is probably 50 pages long. And he gives you the expansion for every coordinate system that you can think of. That's where I learned curvilinear coordinates. He's a chemical engineer. These guys are chemical engineers. And the book is on low Reynolds number dynamics. But the appendix deals only with this curvilinear coordinate system. So now we have a recipe for calculating the metric tensor and the metric coefficients because it's just partial derivatives. And I will illustrate it with an example. The reason why we develop this is if I know that, then I know how to calculate the gradient of a scalar function because they are given in terms of these metric coefficients. How to calculate the curve, again these are given in terms of these metric coefficients. So you can expand these gradients, curves, divergence, etc. in any coordinate system that you want. Okay, that gives you quite a bit of power. Once we develop these equations, we can solve any problem in any coordinate system. Okay, so we are just preparing ourselves to be able to do that. So we should understand what a curvilinear coordinate system is, what are metric coefficients, what is a metric tensor, what is orthogonality of the coordinate system. Any questions on that? Hopefully this example that I'm going to do now will take you through the same steps. We have seen these steps in a very generic fashion. We are going to apply that to a very specific case now. And that specific case is a cylindrical coordinate system. And in the cylindrical coordinate system, the coordinates are r, theta, and z, or x3. Okay? And they are related to x1, x2, x3, the Cartesian frame. Okay? So this describes cylindrical surfaces. Pipes are often cylindrical. So it's a very commonly used coordinate system. Now, I said that there is a relationship between xi as a function of qj or its inverse. In the case of cylindrical coordinates, that's fairly easy to see. x1 is equal to r cos theta. Remember, the 2 coordinates we are talking about are x1, x2, x3, and r, theta, and z. So R, theta, and Z are equal to Q1, Q2, and Q3 in the general case. In the special case, we can figure out if this is theta, if this angle is theta, then x1 is going to be equal to R cos theta, and x2 is going to be R sin theta. This is from simple trigonometry. So this is the relationship we are talking about. When I say x1 can be expressed as function of Q1, Q2, Q3, this is your first equation, second equation. The third equation is trivial. X3 is the same as Z. Z in the cylindrical frame, X3 in the Cartesian frame. So we have the starting point, the three equations, okay, that relate x1, x2, x3 to q1, q2, q3. Now, what are the ranges for q1, q2, q3? In this case, q1, q2, q3 being r, theta, z. R can go from what to what? In the Cartesian frame, what would be the range for x1, x2, x3? From minus infinity to plus infinity in each one of the directions. That's what we need to span the entire space. To reach any point in space, we need to have minus infinity to plus infinity. But in the case of cylindrical coordinates, if you want to reach all the points, what would be the range for r? 0 to infinity. R can never be negative. R is measured from this axis, so it can only be positive. Okay? But you can still reach the entire space. And similarly for theta, what will be the range of theta? Just go one round, 0 to 2 pi. That is, start here, go all the way around, come back, 0 to 2 pi. If you go again, 2 pi to 4 pi, you're going to address the same points. You're covering the same territory. So to cover all the points uniquely, all you need is R to span 0 to infinity, theta to span 0 to 2 pi, and Z, of course, to span minus infinity to plus infinity. So that is the domain of application for each one of these equations. Okay? And I said there is an inverse relation too. Meaning if you give me R, theta, Z, I can calculate x1, x2, x3 from here. But if you give me x1, x2, x3, how do I calculate R, theta, Z? The inverse relationship. Okay? So R equals square root of x1 squared plus x2 squared, theta equals tan inverse x2 over x1, Z equals x3. So these two transformations allow us to go from one coordinate system to another coordinate system. Now we are going to calculate the metric tensor. Okay? How do we calculate the metric tensor? The metric tensor, if you recall, Gij is equal to dxi dq dxk dqi dxk dqj. Summation over all the x derivatives, first with respect to qi and then with respect to qj. So we need to calculate all the partial derivatives, and that's what I've done and assembled in this table. Okay, so this is dx1 dq1, dx1 dq2, sorry, dx2 dq1. That's very simple. So all you want to take this derivative, all you need to do is go to that expression that you have for x1 in terms of this expression. Take the derivative with respect to r, that is cos theta. Take its derivative with respect to theta, you will get then minus r sin theta, because derivative of cos theta is minus sin theta. Derivative of x1 with respect to q3 is 0, because the z does not appear in the first equation. Am I talking fast? Are you guys following? Okay, so from this equation, from these three equations, I've constructed this table. Any questions on that? Do you understand how those tables are constructed? You need to be able to do this. I'll give you a much tougher transformation in your next assignment. And you need to be able to construct this table, construct the metric tensor, do an expansion for divergence, curl, and things like that. Okay, our goal is to get the metric tensor, make sure that the metric tensor is diagonal, which shows that the coordinate system is orthogonal, and then get the diagonal elements. Those are the metric coefficients. You can use them in the expansion. So in order to calculate, for example, G11, what do I need to do? G11, the first term. I is 1 and j is 1. K will take all possible 3 values. Okay? So that means from the table, what do I need to do? Tell me. I have a table of all partial derivatives and I want you to calculate G11. And if I were to write it out, it's going to be dxk dq1 dxk dq1. So you'll put k equal to 1, 2, and 3, and then add them up. So it's going to be dx1 square, dx1 over dq1 square, dx2 over dq1 square, dx3 over dq1 square, right? That's essentially the first column. Take these numbers and square them, multiply it with itself. So it is sine cos theta times cos theta, which is cos square theta, plus sine theta times sine theta, which is sine square theta, plus 0 times 0, which is 0. So when you add that, you will get G11 as cos square theta plus sine square theta, which is equal to 1. So the diagonal element, the first diagonal element will be 1. When I had to calculate G12, what would I do? I will take the first column and multiply it by the second column and then add them up. So it's going to be cos theta times minus r sine theta, then sine theta times r cos theta. Those will cancel out, and then 0 times 0. So G12 is 0, sum of the products of column 1 and column 2. I state here, right? Do the same thing. G13 will be 0. Okay? And then G22 is going to be the same column twice, multiply. So it's going to be r square sine square theta plus r square cos square theta, which is going to be equal to r square. Okay? And if you fill the rest of them, you will find that it is diagonal, and the last one will be 0. So the metric tensor will be something like 1 r square 0, 1, and everything else is 0. That is going to be your metric tensor. All the off-diagonal elements are 0. That assures you that the cylindrical coordinate system is orthogonal. At every point of intersection, the 3 coordinate lines are perpendicular to each other. Okay? And the metric coefficients, which are defined as h squared, if you go back to the definition, here you have to be careful. There are, like, h square is defined as summation of dxi dxi dqj squared. Okay? So h itself will be equal to r in this case, because h square is r square. So the metric coefficient for the cylindrical coordinate system, h1, h2, h3, h1 will be 1, h2 will be r, and h3 will be 1. Okay? And in some books, you will find the metric coefficient defined as the inverse of this. 1 over h1 will be defined as r.
I have a question.
Yeah.
What will we find if the coordinate system that you use doesn't have a tensor that has zeros on the other copy?
Right. If the tensor is not diagonal, that means it is not orthogonal. Okay, so it is still possible to do the transformation in non-orthogonal coordinate systems, but the math gets much more complicated. An example of a non-orthogonal coordinate system for a coordinate system like this, if you have lines like this, you could have. When they intersect, they are not perpendicular, but you can call this as x1 coordinate and that one as x2 coordinate, right? But that won't be non-orthogonal. What it means is whenever you're taking the derivatives, you will have cross derivatives. Like you will have terms like d square v1 over dx1 dx2. If it is orthogonal, then you don't have those cross derivative terms. So it is always nice to strive for an orthogonal coordinate system, but some cases you cannot, and you can still set the problems and solve them, but it gets a bit more complicated. So most in this course we will look at only orthogonal coordinate system. To the extent you may be asked to check whether a coordinate system is orthogonal or not, which means you should be able to construct the G matrix. Now this is something I took from the Wolfram research website. This is the guys who developed Mathematica, and I think Tom gave you an introduction to Maple and Mathematica. So if you go to their website, you will find a lot of these tools on curvilinear coordinate system. Okay, so this is the general expression for gradient of any function phi. and it is simply 1 over h1 d phi du1 plus 1 over h2 d phi du2, etc. So these h1, h2, h3 are the ones that we have been after. We have learned how to calculate these. And so you can expand this gradient function in any coordinate system as long as you know how to get the h1, h2, h3 in that coordinate system. So for example, in cylindrical coordinate system, if you try to expand the gradient of a function, it will be simply I1 times du dr plus I2 times du d theta, but you'll have a 1 over r term plus I3 times du dz. Okay, so the 1 over r term comes because h2, the second one, is metric coefficient is r. And it should also dimensionally be consistent because here you have du dr, there is a 1 over r, du d theta. Theta is not a distance measure, it's an angle measure, right? So that's why the 1 over r makes it consistent dimensionally. Okay, that's another way of kind of validating that. So the same thing applies for divergence and the curl. These are the three operators that we have seen. So if you know h1, h2, h3, you should be able to expand any one of those operators, gradient, divergence, or curl, in any coordinate system. Obviously, you can see the complexity increases tremendously when you go for curl, okay, in non-Cartesian frame. Now, yeah, as I said, for cylindrical coordinate system, you get a 1 over r term there. Okay, any questions or comments? Yeah.
H1, H2, H3 is different if the coordinate system is different.
Yes, for each coordinate system, you should get that h1, h2, and h3. For cylindrical coordinate system, h1 is 1, h2 is r, h3 is 1. For spherical coordinate system, you will have one of them as r squared, for example.
For each, this one, you compare the x. This system is that, so you get h. Just the normal x1, x2, x3 compare with the cylindrical coordinate, so you get h.
Yeah, yeah.
So every if there is a new coordinate system, it's still this way, just like compare x1.
You always start with the Cartesian frame. In developing the relationship, you always start with the Cartesian frame to the new coordinate system, and you get this metric coefficient for that transfer. But
if there's any chance that you compare the cylindrical coordinate with the new one to get h.
But the metric, if it turns out that the new coordinate system that you're constructing is orthogonal, then the metric coefficients are inherent in that coordinate system. So you can expand all these because you won't even know which coordinate system you're coming from, because this is valid for any coordinate system. So all you need is h1, h2, h3 in that particular coordinate system. Then you can expand these. Now I think what you are asking is, I set up a relationship between x1, x2, x3 and q1, q2, q3. Can I go, for example, from r theta z in a cylindrical coordinate system to r theta phi in a spherical coordinate system? Obviously you can. You can develop that relationship explicitly because you already know how cylindrical relates to Cartesian, spherical relates to Cartesian. By simple elimination of x1, x2, x3, you should be able to relate r theta z with r theta phi, and then do the analysis. But typically, this is how it is done from Cartesian to a new coordinate system. And once you get the metric coefficient, they are inherent properties of that new coordinate system. Okay. So if you go through from Cartesian to spherical or cylindrical to spherical, you should still get the same metric coefficients for the spherical coordinate system, because there is a metric coefficient for the particular system. Okay. Okay, I'm not going to spend a lot of time on this, but this simply tells you how to calculate forces on surfaces in various coordinate systems. So here you have a cylindrical coordinate system. If I take a surface, constant r surface, but over a differential element of theta and a differential element of z. then I get the surface to be like this. It's a patch on a cylindrical surface. Okay, so dz would be this distance, and r d theta. This distance would be r d theta. So the area would be r d theta times dz. On that surface, if I want to calculate the stress, how do I do that? Okay, that's what this is taken from Percival and Lightfoot. This expression tells you how to do that. Now you need to make sure that you understand what it is saying, and you should be able to calculate that particular integral, that force. Okay. Any questions on that? If you see an expression like this, or an expression here, or an expression there, make sure that you understand. If you don't understand, ask me now. Yeah, you don't understand that. Okay. Have you looked at it? What is it that you don't understand? It's all Greek symbol, right? It's like the Greek language. Just take it apart piece by piece. What we are trying to do is calculate the stress on a surface. Okay, the surface, as we said, I can have a constant r surface, constant theta surface, constant phi surface, constant z surface, depending on coordinate system, depending on the geometry that I'm interested in. So let's just look at this in particular. Are you able to read what it says? It says minus tau r theta evaluated at r equal to r d theta dz. Now what is tau? Tau is a stress, force per unit area. So I need to multiply by the area. So I need to identify what area on which that stress acts. What do you remember what we said about the first index and the second index of tau? First index identifies the surface. The second index identifies the direction in which the force acts. Okay? That stress has 9 components in all coordinate systems. We saw Cartesian, the same thing applies to cylindrical, same thing applies to spherical coordinates. That tau is a physically meaningful quantity. Its components will be different. Okay? So in this case, what we are saying is, I'm going to calculate the stress on an R surface. Constant R surface is a cylinder. We already know that. Okay. So, for example, I have a cylindrical pipe. Okay, and I have wind blowing on that cylindrical pipe. And I want to calculate what is the force exerted by the wind on the pipe, so that the pipe won't be blown away by the hurricane. I want to apply a restraining force that's large enough. Okay. So I would want to calculate on that cylindrical surface what is the net force exerted by the air that is blowing at a very high velocity. This is the expression that's going to, expression like this is the one that's going to get you an answer to that, because it says I'm calculating tau r on the R surface. Now in this case I'm calculating theta. What does that mean? I'm calculating the force that is tangential to the cylindrical surface. There is also a tau or r, okay, on the same surface. And there is also a tau r z. Okay? So I can calculate all the 3 components of the stress acting on that surface. Of course, we need to know how to calculate the shear stress. That we are going to do later on, okay, in terms of the gradients of the velocity field. If I know how the velocity changes from the surface, I can calculate its gradient, then I know the shear stress. Then when I integrate that shear stress over the entire surface, I get the total force caused by the wind on that cylindrical surface. Okay, that's what this expression means. The same thing here. So here minus tau r theta on the surface, but it is r square sine theta d phi. So what are we calculating? We are calculating on the R surface, again a spherical surface, but in the theta direction. In the theta direction. And the surface area of that element that you see there has to be figured out from geometry. Okay? And these are all listed in the appendix by Happel and Brenner. So that surface area is r square sine theta d phi. Okay? So d theta is in one direction. This is d theta. And that is d phi in cylindrical coordinates. Okay? Is that clear?
That tau r is the pressure?
The tau r.
R.
Good question. That's a very good perceptive question. Tau r, because we are saying that it is on the surface, r surface in the r direction. So his question is it the pressure? The answer is no. Pressure is separately taken out. This is the momentum transfer due to molecular interaction on the r direction in the r surface. So this is part of the shear stress component, but there is a component that also acts normally to that. Okay, separate from pressure. That's a very, very perceptive question. It is, you already recognize that tau r must be normal to that particular surface. Okay, but that is not the pressure. Any other questions? All right, I think let's start developing the equations. Here is a messy coordinate system that I have for you to think about. It's called, I think, an ellipsoidal coordinate system, also taken from Mathematica. Okay, so what is a coordinate system? This is a two-dimensional coordinate system. Okay, so it's basically x1, x2, or xy. So xy grid is basically a set of lines like this. Okay, but what they're saying is I could have any other sets of curves, the intersection of which will give me a point. So in here I have one set of curves that are ellipse that you see here. These are all parts of ellipse. Okay, these are all parts of ellipse. The other one, which are parts of hyperbola, and they all intersect. So that point P I can give you either in terms of this x1, x2, or in terms of the coordinates that are on that curve. So here, for example, I'm going to use, instead of q1, q2, he uses u and v as the two coordinates. Okay, so u equal to 1, u equal to 3 over 2, u equal to 2. That represents a coordinate curve. On that curve, wherever you are, u is going to be 2. Okay. Similarly, if you take this curve, wherever you are, it's going to be v is going to be equal to 5 pi over 3. That's what it is, coordinates. If you go along this line, x2 is a constant. If you go along this line, x1 is a constant. So the same idea, you have a set of a net of curves, the intersection of which gives you the coordinate points. And we can develop the relationship between x1, x2, and u and v. In this particular case, that relationship is this. X equals a cos hu times cos v, and y equals a sin hu sin v. Hyperbolic cosine and sine functions. And the inverse relationship is given by this. Okay? No, sorry. By eliminating, we are showing that this is a relationship between x and y and u and v. Okay? So if I maintain u as a constant, u is a constant, then what does this curve represent? Ellipse. And that's how we draw those coordinate systems. Similarly, if we keep v as constant in the second equation, that represents a hyperbola. Okay, so we can trace those curves from these two equations. And for constant value of u gives you one coordinate curve. Constant value of v gives you an orthogonal coordinate curve that will be perpendicular to it at the point of intersection. Once you have that, this is going to be your assignment. Next assignment, one of the problems is get me these metric coefficients. I give you the starting expression between x and q, and you go through the process of developing the metric tensor and get me these metric coefficients. Not only that, once you do that, you get the expansion, gradient, divergence, etc. in that particular coordinate system. Okay, that's the purpose for which we develop this. Okay, I put down a set of correlations. These are all from Bird, Stewart, and Lightfoot. I'm just going to in general, you should read, of course, a lot. But whenever I say I'm assigning a reading assignment, I'm not going to cover it in the class, but I'm going to hold you responsible for what is in that particular section. In this one, it's basically viscosity of suspensions. If I have, for example, a liquid with fine particles, powder in that. Can I treat that effectively as a fluid with an effective viscosity? And there are empirical correlations that are given to you. Some of them you will derive, okay, later on in the course. So here is for a concentrated suspension, and here is for a fluid. Emulsion, for example, you have oil and water droplets. Okay? Then mu0 and mu1 are viscosities of these two fluids. Previous example was for fluid in a solid. And then you have a charged particles. So for all these things can be treated as effective suspension. You can deal with an effective viscosity. But for now, all we need to know is viscosity is a property that relates the shear stress to the shear rate, which is the velocity gradient, and that linear relationship. Okay? For a pure fluid, you can measure it in a viscometer. But for suspensions, these are some empirical correlations, some of them with theoretical foundation that can be used. So now starts the development of the equations of motion. Okay? So we are going to start developing conservation laws, mass conservation, momentum conservation, that will give us the so-called equations of motion for the fluid, which we will solve later on. Now, in deriving these equations of motions, there are two viewpoints one can take. Okay? And the two books that I'm going to rely on in this course, one is Stewart and Lightfoot, the other one is Kundu and Cohen. Okay? They both take different approaches. So it is actually good for you to see both approaches. And I'm going to do both approaches for different problems. For example, when I derive the momentum equation, I'm going to do in what is called a Lagrangian frame of reference. And when I do the energy equation, mass balance equation, I'll do it in what is called an Eulerian reference frame question. Okay. So first thing we need to discuss is what is the difference between a Lagrangian viewpoint and an Eulerian viewpoint. Okay. In describing nature and in writing down the equations that we want to capture about the nature. The Lagrangian viewpoint is the following. If you have a material that you can tag and follow its motion, okay, then you describe the laws of motion in that frame. So that's the same material all the time that you are observing. Then we call that as a Lagrangian description. So you have an arbitrary material volume. If we call it a material volume, that means we tag all the material. Nothing can come in, nothing can go out of this material volume. So this is called a material volume. So by definition, nothing can come in, nothing can go. It can change its shape. So think of it as a balloon filled with water. And you're throwing the balloon and you're tracking the trajectory of the balloon. Okay? It's the same water that is inside. That would be a Lagrangian description. An Eulerian description is one that Bird, Stewart, and Lightfoot uses. Bird, Stewart, and Lightfoot. This is Kundu and Cohen. You take a control volume, but the control volume is fixed in space. Okay? So material can come in through that, material can leave, and by keeping track of what material comes in and what material leaves, we will be able to balance the material coming in and going out. Okay? So that is a fixed Eulerian viewpoint. A good example, I guess, would be a rocket probe that we are launching to, say, moon. What would be the best description to describe the motion of such a rocket probe? Eulerian or Lagrangian? It's the same rocket that we are following forever, right? So a Lagrangian description, and what we need, of course, its motion. That means we need to be able to predict its position as a function of time, its velocity as a function of time. So initially we give it a thrust, and it is ejected into a trajectory, and we want to predict that. So a Lagrangian description would probably be the best description to write Newton's law of motion. We are going to write Newton's law of motion in both cases, but in that case, motion following that particular material volume would be the best one. Now, I'm studying flow in a pipe, okay, in a chemical plant. I have a pipe that carries crude, and I want to know how much of fluid is, what is the flow rate. because I want to meter. I want to know how much of crude I'm processing. So I'm putting a device, an orifice meter or a venturi meter, a device that measures the flow rate. And that is an Eulerian description, because I'm fixing the location and I'm observing what comes in and what goes out and counting how much of material is going through that. Okay. A more familiar example would be, I don't know whether you have seen these on the roads. You will see some wires sometimes that are placed by traffic department to watch how many cars are going in a particular road to monitor the traffic. Okay, what would that be? Eulerian description, because you are tracking how many cars are passing through a fixed point. Okay, fixed laboratory reference frame. Now, a cop is chasing a single car and trying to find out how fast he's going by using a radar. That would be an example of a Lagrangian, because you are following a particular car in a traffic. Okay, so these are some of the examples of Eulerian versus Lagrangian description. So, yeah. Okay, that question, the answer to that question is you can study any problem in either viewpoints. Because it's easier. If you formulate the problem in the right reference frame, it becomes easier to solve. But you can go from, just like we were developing methods to go from cylindrical to Cartesian, you can also go from Eulerian description to Lagrangian description. From Lagrangian description to Eulerian description. In fact, we are going to do that. Okay? But it is natural and it is easier if you choose the right coordinate system to express a particular problem. And you will see this most powerfully when we develop the conservation equations in a Lagrangian frame. And using mathematics, using transformations, we'll go from Lagrangian to Eulerian reference frame. But it is best to study fluid mechanics in Eulerian reference frame. Why? Because we cannot tag every fluid particle and follow where it goes. We can go in many different directions. So we observe at a particular place how much of liquid is coming, how much of liquid is going, and from that we study the velocity, momentum, etc. So Eulerian frame is the best description for fluid mechanics. Lagrangian description is probably the best one for rigid body dynamics. Okay, but there is a relationship between the two, and one should be able to go from one to the other. Now, in an Eulerian reference frame, we are saying that this is a fixed lab reference frame. Okay, whereas the material frame is a moving one. It is moving with the object. Now, in this case, if I am observing the velocity of a fluid that is going through that, its change in the x1 direction, for example, I will define my conventional dv1 dx1, dv1 dx2, etc. This means I'm keeping everything else constant. These are partial derivatives, right? So when I say dv1 dx1, I'm keeping t constant, I'm keeping x2 constant, I'm keeping x3 constant. Whereas when I take the derivative in a Lagrangian frame, I will write it like this, d dt of v. That means I'm keeping the material constant. It's the same material forever. Okay? And so that derivative is going to be much more complicated in terms of the Eulerian derivatives in an Eulerian reference frame. So the next question that we need to answer is, what is the relationship between the derivatives in the Lagrangian frame and the derivatives in an Eulerian frame? Okay? To give you an example of this, suppose I have a thermocouple in my hand, okay, and I'm measuring the temperature of air at a particular point. So I have fixed the thermocouple, wind is blowing, but I'm measuring the temperature as a function of time over a period of time, and I create a chart, and the chart gives me temperature as a function of time. Okay, and I get a curve like that. If I take the derivative of this at any particular point, what I can get from this is dt at that particular position vector, at that particular location where I have kept the thermocouple. So that is an Eulerian derivative, a partial derivative of how fast the temperature is changing at that particular point. Okay, that would be an Eulerian derivative, rate of change of a particular quantity. The next example I want you to think about is the following. I have a skydiver who is flying on a plane, and he has a thermocouple in his hand. And he jumps off the plane. Okay, and he has a recorder. So as he falls, he records the temperature. So when he comes down, he gives you a chart of temperature versus time. That looks something like this. What is the relationship between this chart and the chart on the right hand side? On the right hand side, I measured the velocity, the temperature at a particular point, fixed point. That is Eulerian. Okay. In here, I have a derivative of temperature with respect to time, but that contains information about how fast the temperature is changing, not only with time but with position, because he is moving through the position. But it is the same material volume, meaning it's him that I'm following, or the thermocouple at his hand. Okay, so that temperature is going to be a function of the position and the time. That is, at a particular time, he would be in different positions. This x itself will be a function of time. So I should actually write this as x as a function of time, and also him as a function of time. So that kind of information is encoded in this temperature chart. So when I'm taking the derivative of that temperature, instead of v, let me put as temperature, what I'm really taking is a derivative of that temperature with respect to time, keeping the position constant, it's a vector, plus how fast the temperature is changing with position, dt dx1, dx1 dt, plus dt, I'm simply applying the chain rule. But conceptually, I'm understanding what is happening and then applying the chain rule to that. So it is dt dx2, dx2 dt, plus dt dx3, dx3 dt. And this I can just write it. Chain rule. Okay? So that total derivative, that chart that he gives me, and if I take the derivative of that chart, I am actually capturing this entire information. Okay? And this is called a substantial derivative, Lagrangian derivative, total derivative. There are different names given for it in different books. Okay? But that contains the information not only of temperature change with time, but temperature change with position, and what is dx1 dt? The velocity of the skydiver. dx1 dt is the rate of change of position with respect to time, right? So you would actually see this written as dt dt plus v1 ddx1 of t plus v2 ddx2 of t. Right. You can see it's a cumbersome way of writing it. So if in index notation, you can write this elegantly as d dt plus vi d dxi of t. Or in Gibbs notation, you can write this as d dt plus v dot del t. Okay, so that is called a substantial derivative or the total derivative following the motion. Okay, I think there is another example in Burstiver and Lightfoot where he's talking about fishing in a river. Okay, so if you anchor your boat at a particular point and then measure the concentration of fish locally, you are measuring the Eulerian observation. So if you take derivative of that, you are going to see how fast fish concentration is changing at a particular location. But if the boat is drifting with the river and he's still collecting samples of fish and measuring the concentration, that concentration change as a function of time is going to depend not only on the local variation in space and time, but the boat itself is moving. So the velocity of the boat will have an influence, just like the velocity of the skydiver in this case is having an influence on that observation. Okay, so that is the difference between an Eulerian viewpoint and the Lagrangian viewpoint. So let's try to derive this equation of motion in a Lagrangian viewpoint for mass conservation. I didn't put the notes on this in a typed form, but I will put a written up version of it on Moodle. So you don't still have to write it up, just pay attention to it. So the first thing that we're going to develop is the conservation of mass. Let me see. now you will know why I prefer to type it out. My handwriting is really terrible. Conservation of mass. So we're going to do this in a Lagrangian frame. So this is my material volume. Okay, and how do I calculate them? And I tell you that rho is the density of the fluid in that material volume. Okay, rho is the density and Vm is the total volume. The density could change from point to point. So this is an arbitrary material volume with an arbitrary fluid there. So how would I calculate the mass of it? Rho is the density and Vm is the material volume. So if m is the mass, how would I calculate the mass of that material volume? Rho, you take a small elemental volume there. The density in the small elemental volume is rho, multiplied by dV, that elemental volume, and then integrate it. Integrate it over what? Over the entire material. Okay? This is the important part I cautioned you about before. Understanding the concept and translating it to symbols and mathematical language. That's what we are trying to do. So we are trying to estimate what is the mass in a material volume like that if you give me the density distribution inside the material volume. So I take a small elemental volume and find out what is dm, and then I integrate it over the volume. So that's by definition. Okay? And then I do the integration on both sides. On the left hand side I get the total mass. On the right hand side I have it as integral of Vm over Vm of rho times dV. What does mass balance tell us? Mass is neither created nor destroyed. Mass is conserved, right? Except in nuclear reactions, mass is conserved. So what does that mean? If I take following the motion, suppose this material volume is not stagnant, it's not in laboratory, it's moving freely. Okay? So it can change its shape, but it has the same material forever. That is how we define a material volume. So if I say, what is the rate of change of that material volume in the Lagrangian sense, what would that be? 0. That's how simple it is to write the material balance equation in a Lagrangian frame. Okay? So, but the definition for d dt here is the derivative following the motion of that particular material volume. It doesn't change because nothing can enter, nothing can leave that particular material volume. So, by definition, dm dt equal to 0. Okay? So that means I need to add a page. How do I do that? My apologies. Just give me a minute. I'm trying to figure out how to add a page. What do I do? Is this one? Okay. Okay. So this can be written then as d dt of whatever expression I had for m, which is integral of rho dv. That is equal to 0. Okay. Now we are going to use something called the Reynolds Transport, which is a result from calculus that relates, we have already seen the Leibniz rule, okay, which relates the derivative of an integral. This is the same relationship in a Lagrangian frame of reference, and it goes like this. That is, if I have d dt of any quantity alpha dv, okay, that's going to be given by integral of d alpha dt dv over the same volume plus integral over the surface area of that material volume v dot n dA. Okay, it's called the Reynolds Transport theorem, which is a general result. It doesn't have anything to do specifically with fluid mechanics. Any quantity alpha, alpha can be a scalar, vector, or tensor. It simply says the derivative of the integral of the function is integral of the Eulerian derivative. Here it is a Lagrangian derivative. On the right hand side, this is the Eulerian derivative. And then what happens to the surface? How fast the surface is deforming? For example, V dot n is what? What will you give the interpretation of V dot n? Normal velocity of that surface. Okay, if that is the n, if this is v, v dot n is going to be saying how fast that interface is deforming, moving in the normal direction. Okay, and you do that integration over that surface of the material surface, and that is the relationship. So all we have to do now is use that Reynolds Transport theorem on our mass conservation equation. Okay, so you'll be able to go from material derivative to Eulerian derivative. The theorem is essentially generalization of what we saw as Leibniz rule in the last lecture. For Leibniz rule we saw in a fixed Eulerian reference frame. What did it allow us to do? It allowed us to calculate the derivative of an integral, which is given by the integral of the derivative plus how fast the boundary is changing. Maybe I should put that up. I think I probably have that at the top of this lecture. Okay, here. This is essentially the result that I'm talking about. Okay, d dt of any quantity over the volume is equal to integral of the rate of change of that quantity with respect to time plus the normal component of that velocity, the surface velocity, multiplied by the same quantity Tij. This is the Reynolds Transport theorem. Okay, so in our case, we need to figure out what that quantity is going to be. Here I took that to be a stress tensor, but it could be a scalar, it could be a velocity, it will apply to all the quantities. Okay, so all I'm doing is I'm applying that particular theorem that relates the total derivative and the derivative of an integral to integral of a derivative. That's what allows me to go from a Lagrangian description to an Eulerian description. So this is a partial derivative, whereas this is a total derivative. Okay, so the connection that we need to make in the present case is that we have d dt of rho dv equal to 0. So what would this be in our case? Rho. Okay, and then you will have this mkwk, which is n dot w. Here I call the w as the surface velocity, but in the other case I'm calling v as the surface velocity. So it's essentially application of this particular expression to that equation that we've seen. Okay, so if you go back to this, so this is going to be, now we're going to apply this theorem to this particular expression. So it's going to be integral over Vm of d rho dt dv plus integral rho dA is equal to 0. Okay, so this is the mass balance equation. By applying the Reynolds Transport theorem, the mass balance equation becomes this. Okay, and this you should be able to do because we're going to repeat this again when you do the momentum balance equation using the Reynolds Transport theorem, using the Gauss divergence theorem. These two we will use. What does the Gauss divergence theorem do? Do you remember? We saw it in the last class. It relates a surface integral to the volume integral. Okay, so now we need to use the Gauss divergence theorem. Okay, and what you will get is, so that allows us, sorry, here I have a mistake. This is the surface area. Okay, so now I will have Vm d rho dt dv plus the Gauss divergence theorem says what? the surface integral is the same as the volume integral operated on del dot rho v dv equal to 0. So here I'm combining this rho and v, and that is dotted with n. So whatever that product rho v goes inside the divergence term. That's what the Gauss divergence theorem dictates. Okay. Now we notice that both of them have been expressed in terms of that material volume, the same material volume. So I can take the integral as a common factor and write it as d rho dt plus del dot rho v dv equal to 0. Okay. But Vm was arbitrary. We started off with an arbitrary material volume, right? So how can that integral be 0 for any arbitrary material volume? Only if that integrand is identically equal to 0. Do you understand what I mean by that? The only way I can satisfy that equation is since Vm is arbitrary, we have as del dot rho v is equal to 0. That is the continuity equation in an Eulerian reference frame. So we started from a Lagrangian frame. Using Reynolds Transport theorem, we went into the Eulerian frame. And using the fact that Vm is arbitrary, we are insisting that the integrand is equal to 0. Do you understand that argument? Why should that integrand be 0 since Vm is arbitrary? If not, I can give you this example. Suppose I have an arbitrary function between certain limits, okay, and I want that integral of that function to be equal to 0. Some specific instances I can pick a curve and the positive and negative will cancel out for specific situations. But if it is arbitrary curve that I pick, a curve that I pick like this, it's not going to be equal to 0. The integral is not going to be equal to 0 unless that function itself is 0 everywhere. That is the argument we are making. This function that I identified in square brackets must be 0 everywhere because the material volume is arbitrary. Okay? And that's how we get this equation. Let's look at the assumptions. What are the assumptions we have placed in deriving this equation? Did we say, is it compressible or incompressible, gas or liquid? We didn't make any statement about that. Okay? So it is valid for all kinds of fluids that you can think of. Okay? So it is valid all fluids. But if it is a compressible fluid, density is no longer a constant. Okay? So you need to have an equation of state that relates the density to pressure. Pressure, of course, will be coupling in the momentum equation because it deals with force. Here we are just saying this is satisfied, mass is conserved. That's all we are enforcing. Okay? So if rho is constant, then we call such fluids as incompressible. Okay? Then we will have rho as a constant. So the equation will simplify to del dot v equal to 0 because rho is constant. So the derivative drops out and the rho inside this can be taken out and that cannot be 0. So del dot v equal to 0. So for incompressible fluid, the mass balance is simply the divergence of the velocity field is equal to 0. This is why we introduced this idea of a gradient and divergence, etc. Now we can talk about a physically meaningful equation, which is the continuity equation. So if del dot v is 0, that means continuity equation is satisfied by that velocity field, the three-dimensional velocity field. Okay? So this is a very important equation called continuity equation. Sometimes it's called the divergence-free condition on the flow field. Any questions? Okay. The next thing that we need to do is apply the same idea to develop the momentum balance equation. Okay, in a Lagrangian frame. Okay, so what is the momentum balance equation? Linear momentum balance. Newton's law. What does Newton's law say? Mass times the acceleration, F equals ma. A is a vector, F is a vector, right? That's what basically Newton's law says, that there's an equivalence between acceleration and the force that you apply. But we need to apply this to a fluid system. Okay? So what we need to do is we need to take a material volume once again, Vm. If we know the material volume, we can calculate its mass, so we can calculate its momentum. We can express its rate of change of momentum. But what we need to worry about is what are the external forces that are acting on this material volume? What are the forces you can think of so far from what we have seen? Gravity, which is going to act on the entire volume because it is a volume force. Okay? Buoyancy is a consequence of pressure variation. So buoyancy is not a fundamental force in that sense. Okay? So gravity is a fundamental force that we need to include in this. And the other force that we need to include is pressure and shear forces. A pressure force that would act normally, for example, and a shear force that would act tangentially on my material volume. The material volume simply says there is no material entering or leaving. Doesn't mean that I cannot apply stresses to it. What is your question? Okay. So we can apply a tangential stress. We can apply a normal stress. We cannot inject material into it, but we can apply a force. We can squish it. We can make the fluid inside move by simply rubbing it, for example, in a tangential direction. All those are possible. So we're going to consider two types of forces. One is gravity. The other one is shear and pressure forces. Both of them have origin in intermolecular interaction. And since we are not looking at it at the molecular level, we're looking at it at a continuum level, this is the only force that we need to worry about. The drag force, the buoyancy force, the lift force, etc. will all come out as a solution to this equation of motion applied to a fluid system. So in the next class, we will derive the specific form of the equation of motion, the dynamic equation of motion. Okay, so please do go through either one of the book, whatever book that you have, go through them to reinforce these ideas. If you don't do that, it's going to get difficult very soon. You need to keep up with the lecture. How do you find the assignment? Has anybody started doing it? Is it fairly easy or difficult? Or okay? Good. It's okay? Good. Good. I'm glad to hear that. That's